Hi friends, in this video we are going to discuss about the concept of EMF equation of a ideal transformer. Okay, so EMF equation of a ideal transformer. Okay, so we are going to discuss about the EMF equation of a ideal transformer, and we know that for ideal transformer, for ideal transformer, so what are the key points we need to consider? So point number one is the value of resistance R in the primary and secondary winding are neglected. Okay, so here the resistance values are neglected. The resistance values are neglected. Point number two is core losses are neglected. Core losses are neglected, and here the value of R is neglected means, so due to the value of resistance we are going to get some losses in the primary and secondary winding of a transformer. So those losses we are calling as copper losses. Okay, so due to the value of resistance we are going to get the value of copper losses. Okay, copper losses, and formula we are using for the primary side, so we are using I1 square into R1, and in the secondary side we are using I2 square into R2. So these two are the formulas we are using to calculate the copper losses in the primary side and secondary side of a transformer. And here core losses, so core losses are always occurred due to the transformer core, and these losses are mainly divided into two types, and core losses mainly divided into two types. So first one is hysteresis losses. Second one is eddy current losses. So here second one is eddy current losses. It means for ideal transformer the value of resistance in the primary side and secondary side we are neglecting, means we are neglecting directly, we can say that copper losses are neglected in the primary side and secondary side. And coming to the secondary side, core losses are also neglected in the transformer, ideal transformer, and these losses are always occurred due to the transformer core, and these core losses are mainly divided into two types. One is hysteresis losses and the second one is eddy current losses. Okay, so these points are we are going to consider for the ideal transformer case. But whenever we are going to comparing the ideal transformer with the practical transformer, definitely we are going to see some losses due to resistance value, and also definitely we are going to get some losses due to the transformer core. That is the reason why in ideal transformer input power is equal to output power. But in case of practical transformer, input power not equal to output power, because ideal transformer do not have any losses, but practical transformer having losses. That is the reason why whenever we are going to talking about the ideal transformer, so we need to consider these points. Okay, with the help of these points only we can analyze the ideal transformer, and also with the help of this analysis we are going to get the electromotive force equation. We can also call it as in shortcut that is EMF equation of an ideal transformer. Okay, now we are going to getting the transformer EMF equation. Okay, so for that we know that already we discussed in the previous video about the working principle of a transformer. If you know the working principle of a transformer, then only it is very simple to understand how we are getting the electromotive force expression from the transformer. Okay, anyway, just see here, I am going to drawing the transformer diagram. Now this is a transformer core, and here we have two different types of windings. The source we are connecting, the voltage source we are connecting to the winding we are calling as primary winding, and the load we are connecting to the winding we are calling as secondary winding. Okay, secondary winding, here we are connecting the load. Okay, so this one is the diagram of a transformer, and we know that, for example, V1 is the applied alternating voltage, then definitely due to this alternating voltage, some amount of alternating current is flowing through the winding, and here N1 represents the number of turns in the primary side, N2 represents the number of turns in the secondary side. Now see here, whenever we are applying V1, that is alternating voltage, to the primary winding, there is a flow of I1, that is alternating current, through this particular winding. Whenever this alternating current is flowing through the winding, there is a production of MMF. There is a production of MMF. Here MMF means magnetomotive force. Here MMF is always the product of current into the number of turns in the primary winding and secondary winding. Okay, for example, if I am going to writing the expression from for the primary side, that is MMF in the primary side, that is 1 represents the primary. Okay, MMF 1 is equal to I1 into N1. For example, if I am going to see the MMF in the secondary side, then we can directly write I2 into N2. Now whenever this alternating current is flowing through the primary winding, there is a production of some magnetomotive force, that is the product of current and the number of turns. Whenever we are going to get the MMF in this particular winding, then there is a production of alternating flux, and we are giving the letter for that flux is phi. And whenever this alternating flux is generated in the transformer core due to the current which is flowing through the primary winding, then due to the interaction between this alternating flux and the number of turns in the primary, there is a production of EMF, and here that expression is equal to, for example, we are talking about E1 is a EMF produced in the primary side, then E1 is equal to minus N1 into d phi divided by dt. Okay, so this is the expression of EMF which is produced in the primary side. And for example, if I am going to write the expression for EMF generated in the secondary side, then minus N2 into d phi divided by dt. Okay, so these two expressions are the EMF expressions in the primary side and secondary side, and this EMF is always generated across this particular winding, and here E1 represents the EMF generated in the primary side, and here E2 represent the EMF generated in the secondary side. Now see here, actually if you want to get the EMF in the primary side and in the secondary side, actually what we required, we required the alternating flux. Okay, without alternating flux, it is not possible to get the EMF expression or EMF in the primary side and secondary side. Okay, this alternating flux we can also called as change in flux. Okay, change in flux. Change in flux means what? Flux value is always changes with respect to time. That is the reason why change in flux we are writing here. Change in flux we are writing here, that is d phi represents the change in flux with respect to change in time. D phi represents the change in flux, dt represents the change in time. So change in flux means what? The flux which is always changes with respect to time. So that is the reason why here E1 is the EMF generated in the primary side is equal to minus N1 into d phi divided by dt, and here in the secondary side E2 is equal to minus N2 into d phi divided by dt. Okay, here N1 represents the number of turns in the primary side and N2 represents the number of turns in the secondary side. But here we need to concentrate on one point, that is why we are getting here negative sign instead of positive sign. Okay, why we are writing negative sign here and instead of positive sign, why we are writing here negative sign? Here negative sign represents whatever the EMF is generated in the primary side and secondary side, that particular direction of EMF E1 is always opposes the applied force, or we can also call as what? Applied voltage. That is the reason why we can write here V1 is equal to minus E1. Okay, V1 is equal to minus E1. It means what? Actually the generated EMF is always opposes to the applied voltage. That is the reason why negative sign represents the opposite direction of a E1. Okay, so that is the reason why we are writing these two expressions with the help of negative sign. Okay, please remember negative sign represents the direction of EMF is always opposite to the applied voltage. Okay, that is the meaning of negative sign. Okay, anyway, how we are getting the expression of E1 and E2 in the negative side. Now see here, in this expression, E1 is equal to minus N1 into d phi by dt. Here, we know that without change in flux, it is not possible to get the exact equation of a EMF. That is the reason why here, so alternating flux generated in the transformer is given by phi is equal to phi max into sine omega t. Okay, assume this is equation number 1. Okay, so this is the alternating flux expression. With the help of this expression only, we need to get the exact EMF equation of a transformer in the primary side and secondary side. Okay, so up to this point we discussed about the principle of operation of transformer, and how we are getting the EMF expression from the primary side and secondary side, and what is the alternating flux expression of a transformer. Up to this point is clear. Now here omega represents, omega means 2 into pi into f, and here phi max represents maximum flux, and this flux having a unit is always Webers, and here omega is equal to 2 pi f, where f is equal to frequency, and which is always measured in hertz. Okay, this is always in hertz. Up to this point is clear. Now we are going to enter into the actual concept, and in order to get the exact EMF expression, we need to take the help of these two expressions. Okay, E1 is equal to minus N1 into d phi by dt, E2 is equal to minus N2 into d phi by dt. So that is the reason why we are writing, that is here the EMF E1 and unit of this EMF is always in volts. Okay, EMF E1 in volts in the primary side, is given by, okay, is given by, so E1 is equal to minus N1 into d phi by dt. Now we know that phi is equal to phi max into sine omega t. So that is the reason why instead of this phi, I am substituting this complete expression. So E1 is equal to minus N1 into d divided by dt of, instead of pi, I am writing phi max into sine omega t. Now we need to differentiate this phi max into sine omega t with respect to t. So that is the reason why now you can observe that minus N1 is always constant value, and here phi max is also constant value, and here d divided by dt of sine omega t. Okay, now you can apply differentiation, so that is minus N1 into phi max into d by dt of sine omega t means cos omega t with respect to t. That is the reason why you will get omega. Okay, now here we are writing E1 is equal to minus N1 into omega into phi max into cos omega t. Okay, now here negative sign is there. Okay, negative sign is there. Now what I am doing actually, in order to avoid this particular negative sign here, what I am doing, instead of cos omega t, I am going to write minus sine omega t minus pi divided by 2. Okay, just I am writing, instead of cos omega t, I am writing minus sine omega t minus pi by 2, because we have a formula. So here E1 is equal to, so minus N1 into omega into phi max into cos omega t. Instead of cos omega t, I am writing minus sine omega t minus pi divided by 2. Okay, so here I am writing E1 is equal to minus plus, so that we can write N1 into omega into phi max into sine omega t minus pi divided by 2. Okay, so this is the expression of what? E1. Now we can say that sin omega t minus pi by 2, sin omega t minus pi by 2. If this value sin omega t minus pi by 2 is equal to 1, then that expression, or we can also call it as when the value of sin omega t minus pi by 2 is equal to 1, then that particular condition represents maximum EMF produced in the system. So that what we are doing here. So when the value of, when for example I am taking if condition, so if sin omega t minus pi by 2 is equal to, for example, 1, then in that case we are going to get the value of E1 is equal to N1 into omega into phi max. Okay, because sin omega t minus pi by 2 is equal to 1 means you will get the expression of E1 is equal to N1 into omega into phi max. So this particular formula or this particular condition represents so maximum EMF equation. Okay, maximum EMF equation of a transformer. Okay, and up to this I think clear. Now what is the remaining step? The remaining step is we need to, for example, when I'm going to discussing about the problems, we always consider, or always we are going to calculating the value of EMF in terms of RMS values. Okay, so that is the reason why what I am doing here, I am going to calculate the RMS value also. So RMS value of a EMF E1. Okay, so RMS value of a EMF E1. So we know that whenever we are going for the RMS value, simply we can divide with root 2 for the actual value. So that is the reason why what I am doing here, RMS value, that is instead of small e1 I am writing capital E1, because here capital E1 represents the RMS value of a EMF E1. Okay, so here E1 is equal to so N1 into omega into pi max. Okay, so N1 into omega into pi max. So this is the value of actual original value, and here what I am doing here, I am simply dividing with the root 2. Okay, simply dividing with the root 2. Now here E1 is equal to N1 into, we know that omega means what? Omega means 2 into pi into f, and here the value of maximum flux, that is phi max, we are directly placing here, and here we are having root 2. Now here E1 is equal to numerator consisting of 2, denominator consisting of root 2. So that is the reason why instead of root 2 I can directly write root 2 into root 2. Okay, instead of 2 I can directly write root 2 into root 2. Root 2 into root 2 means again you will get 2 only. So that is the reason why instead of 2 I am writing root 2 into root 2 into N1 into pi into f into phi max divided by root 2. Here 1 root 2 and 1 root 2 gets cancelled. Then E1 is equal to root 2 into N1 into phi into f into phi max. And we know that E1 is equal to root 2 into N1 into, here the value of pi is 3.14, and here f is always f only, and this one is phi max. If I am going to multiplying root 2 into 3.14, you will get 4.44. Okay, you will get 4.44. So that is the reason why I am multiplying directly that particular value. Then E1 is equal to, so root 2 into 3.14 means you will get 4.44 into N1 into f into phi max. Okay, so this is the EMF equation of a EMF equation in the primary side of a ideal transformer. Okay, so this is a EMF equation of a transformer in the primary side. Okay, now we know that again we have what? We have the secondary winding for that particular transformer, and the production of EMF E2 in the secondary side also same procedure. Whenever the alternating flux is linking with the number of turns in the secondary side, again there is a production of what? EMF E2 in the secondary side. So that is the reason why procedure is same for both the EMF E1 in the primary side and E2 in the secondary side. That is the reason why I am not going to derive all the story for the secondary winding. So anyway, we will get same expression, just instead of N1 you will get N2. Okay, so that is the reason why the EMF E2 in the secondary side, it will given by 4.44 into, just you will get N2, because N2 is the number of turns in the secondary side. So N2 into F into phi max. Okay, phi max. So these two are the EMF equation of a primary side and secondary side of a ideal transformer. Okay, this part is the EMF equation of a point. Now see here, if I am going for the one important note, because whenever we are going for the analysis of a equivalent circuit diagram of a transformer, we need to consider one most important concept, that is transformation ratio. Okay, so in order to get that particular transformation ratio, if I am going to consider these two expression and I am dividing E1 and E1 divided by E2, then you will get the transformation ratio for both this condition. So that is the reason why what I am doing. So E1 divided by E2 is equal to 4.44 into N1 into F into phi max divided by here 4.44 into N2 into F into phi max. Here we know that 4.44, 4.44 both are common, so we are cancelling, and here F and F both are cancelled, and here phi max and phi max both are gets cancelled. Then the remaining terms are E1 divided by E2 is equal to N1 divided by N2. Okay, so this is the transformation ratio of a transformer. Okay, so thank you so much for watching, and please do subscribe my channel for more updates. Thank you.